month of the New Year's. So,
Oh my gosh.
Not yet. 2 more days.
yeah.
Two more.
Yeah, tomorrow doesn't matter. I'm
Like,
I'm excited. 23 is going fast. Excited.
it's been a month.
Doesn't matter. That's
Okay, guys.
1/12 of the
Integration by substitution. So as we have been doing integrating, I have been hinting, because some of you guys are like, how do we integrate this one? How do we integrate this one? And it's baby steps, right? We're learning, step by step. And some of the ones we are going to see now are ones that, oh, okay, I didn't quite get how to integrate before. Now we'll start to see it all come together. Now, integration with use substitution. Okay, that's essentially what it is. We're going to do some substituting to make some of these more difficult integrals appear easier so that we can work with them. As we go through this, you will, some of them, the more we practice with, you'll be like, oh, I don't really need use substitution for that. Because this whole idea that I've been saying, okay, there's a chain rule you have to think of, so we have to compensate, right? Like if there'd be a chain rule of times 2, we'd have to put a times 1/2 out front or something to compensate. So, or the idea of balancing it. The use substitution is going to help us do this. As you start to see it more, I'm not saying you're going to necessarily have to use substitution every time. Okay? If you go watch, if you watch an AP Calc video or something, you've got someone that, in Calc, like a professional Calc person is what I feel like saying, they're not always going to use substitution. Okay? I'm going to use substitution more in front of you guys than I ever would on my own. But it's just as you get to see it more, it'll make more sense. Okay? At least I hope it will. That's the plan. Okay? Okay, so the key to use substitution is finding a piece of the function whose derivative is also in the function. So we're specifically working with those chain rules. Okay? The derivative is allowed to be off by a coefficient, but otherwise must appear in the function itself. The role of substitution in integration is comparable to the role of chain rule. So we're using that use substitution to undo chain rule. So a basic procedure here. Look for a piece of the function whose derivative is also in the function. If you're not sure what to use, try the denominator or something raised to a power of the function. Again, that part comes with practice. The first few of these, you're going to look at them and say, I don't know what to pick for you, but you'll start to see it. Set u equal to that piece of the function and take the derivative with respect to the variable. And then you'll use your u and your du, so the derivative expressions, to replace parts of the original integral. And your new integral will be easier to solve. The idea when we replace the old integral is everything in the old integral has to be replaced with something in the new integral. Okay, so all the pieces have to be there. Substitution is a method of integration designed to undo the chain rule. Generally involves 3 steps. First one where you pick what your u is. I guess then they show integrating. And then the key with use substitution here, depending on what part you're at, you do have to often remember to substitute the original part back in. If they give you a problem in terms of x, you don't give your answer in terms of u. Okay, so you have to go back and put those x's back in, at least on indefinite integrals. Definite integrals, when we have numbers to put in, we can talk. There's a couple of different options when we get there. Okay. Down here, there's just some general information. It's just kind of talking about pattern recognition. So being able to, again, look for, oh, well, there's a sine. Oh, there's a derivative of cosine. Or which way do we make it work? Those type things. So, yeah, moving on. Okay, so pick things that you can find the derivative of, or the derivative of, but only different by a coefficient, so by a multiple of some number. Okay, because numbers, I can compensate. If there's a 2 that I need to be in there that's not in there, then I can throw a 1/2 in there to balance it out, those things. Okay, but the variable pieces have to be there. That's the key. So the suggestion was pick things that are in the denominator possibly, or pick things that are in powers possibly. So as we look at A, the integral of x squared plus 1 squared raised to 2x, or times 2x dx. Now technically, it says to integrate by use substitution. Technically, if we really wanted to, could we FOIL this out and multiply by 2x? You could. Okay. I'm assuming I used use substitution here since that's what's in the directions. But you technically could. It would get uglier. Okay? Because there you're going to FOIL, multiply by 2x. I guess once you got multiplied out it wouldn't. But, so, use substitution. You want to take a guess or am I telling you? What are you guessing you could be? No denominator, so you can't pick something from the denominator. Is there something in a power? Well, it has to be something that's physically here. And we have an x squared plus 1 that is raised to a power. In other words, I'm trying to pick something that I want to make u. Then we're going to change this problem to be in terms of u. And so I'm going to pick x squared plus 1. And I'm picking x squared plus 1 because it's raised to a power. And my brain's also thinking on the side, oh, hey, what's the derivative of x squared plus 1? Do I see that in the problem? Does that make sense? That's my brain thinking on the outside. Okay, so right here, I'm going to make that u. Okay, and we'll rewrite this here in a moment. Now, before we rewrite it, we need to take the derivative of u. And so we're going to take the derivative of both sides. Now, the derivative of u, with respect to u, is just going to be, the derivative of u is going to be 1. But then with respect to u, I'm going to say du. So that left side will always be du here. What's the derivative of x squared plus 1?
2x.
2x.
Plus c. Wait.
No. Save the plus c's for integrals. We'll get there at the end. But with respect to x, so I'm going to say dx. And here's the deal. Integrals have dx's in them, right? We have to make sure everything matches up. Now, with this in mind, right here, we have u, yes? We have the u there, and it's going to be u to the second. What else do we have that has to match up somewhere? We have 2x dx. What just so happens to equal 2x dx? A du, yes? So my integral is now going to change. I'm going to change it to u. It's going to become u to the second du. Okay, and keep in mind the du dx, that is the part that's saying, okay, with respect to this variable. Are we in agreement that everything is covered? All of my original integral is part of my new integral, yes? It was x squared plus 1 quantity squared. Well, x squared plus 1 became u quantity squared. There's a 2x and a dx, which just so happen to be part of my derivative, which I can replace with du. Can you integrate u squared? Yes? Piece of cake. What is the integral of u to the second? One-third u cubed. And you can tack it on now, or you can wait till later. But don't forget it. What am I talking about? A plus c. And I say you can tack it on now or tack it on later because, am I done? No. My original problem was not in terms of u. My original problem was in terms of x. So now go back and sub. What is u? U was x squared plus 1, right? So now instead of saying 1/3 u to the third, I'm going to say 1/3 x squared plus 1 to the third plus c. Because right now we're just working with indefinite intervals. Okay. Questions?
So that's your final answer.
That's my final answer. I underlined it. Okay, like, used to be I boxed it. That's your clue. That's my final answer. Right. We're not happy with that final answer, are we? There's a lot of unsure looks out there. I mean, it's, it's just integrating something. If we had FOILed this out and multiplied the 2x in, if we FOILed this out, it should all match up. I'm not going to take the time to do that, but, Okay. Ready to try B? Because here's the deal. You've got to start guessing what to pick. Now, see, this is one I wouldn't necessarily use U substitution on my own. But we need it right now. I'm not saying we don't. I'm not saying, oh, we shouldn't use it for that reason. Okay. In this case, the other, earlier we looked for the inside of a power. Now I'm going to look for the inside of a function because there's a cosine there, right? But is there a sign in the problem? So I don't want to use my U as cosine because there's no sign in the problem. I need to have a sign in the problem if there's a, because my derivative of cosine would have a sign in it. So what's the inside of my function? The inside of my function is 4x, yes? So I'm going to come over here to the side. This is my side work. U is 4x. Take the derivative of that. The derivative of U is just going to be du. What's the derivative of 4x? Okay, derivative of 4x is 4 times dx. Okay. Now, the key is, does everything match? See Peyton shaking her head like, yeah, she thinks it matches. Yeah. Okay, so this right here, it was cosine of 4x, except what are we using for 4x? We're going to use u, right? So that's the function, that's fine. And then what's the other piece here? There's a 4 and a dx. What just so happens to equal 4 dx? A du. Okay, so do you know what to write as your new integral? Instead of cosine of 4x, I'm going to say cosine of u, right? And then 4 dx is replaced with the du. Everything is covered, right? I'm going to have every last little bit covered. So now I'm integrating cosine u. What is the antiderivative of cosine u? I wrote down sine. Positive or negative? Positive. Okay, so the integral or antiderivative of cosine of u is sine of u. And again, I don't care if you tack on the plus c right now or if you wait. Am I done?
No.
No? What's my final answer? Sine of 4x plus c. And as a side note, how can I check myself? Can I take my final answer and take the derivative and work backwards? What's the derivative of sine of something? Cosine of something times what's the derivative of something? Derivative of 4x is 4. It matches, doesn't it? It should always match. Just like I could have had us do that over here. What's the derivative of something raised to a third? Multiplied by the 3. 1/3 times 3 is going to cancel, right? Subtract 1 from the power, and there's your squared. And then what's the derivative of the inside? And that's at 2x. So you can always work backwards, too. Okay? C, if you will. What are you picking to be u? Good. 4x squared plus 1, because it's the insides. Then we're going to take the derivative, yes. Derivative of u is du, derivative of 4x squared plus 1. 8x and then times dx.
So those only work in certain problems.
The problem has to be set up right for it to work, yes.
Okay.
Will u substitution always work for every single problem we do from here on out? No. I mean, in all honesty, there are problems we're going to run into that just aren't integratable by hand. They require the use of the calculator. Okay? But all the ones we're going to see today are designed to somehow work with u substitution. Okay. Is everything matching up? Are you starting to see that when I ask, is everything matching up? Because that's important. If something doesn't match up, we have to figure out why and how to fix it, or if it's fixable. So I want you guys to tell me. Square root of u? Or what I'm actually going to write is u to the 1/2. And then what do I need to tack on? Du, yes? Because everything matched up, right? 8x dx was the du. And then here, 4x squared plus 1 is your u, and it's the square root of u, or in other words, the u to the 1/2. Am I selling you on this yet? Slowly? Okay, there's just a lot of hesitant looks. Okay, did you finish this up? Add 1 to the power. Divide by that power, or multiply by the reciprocal. 2/3 u to the 3/2. Put your original problem back, or your original u value back in. So 2/3 times 4x squared plus 1 raised to the 3/2 plus c. In all honesty, I feel like my answers are usually left like that, as opposed to going back to square root function form. If you had to go back to square root form for some reason, this would be the square root of 4x squared plus 1, and then be raised to the power of 3. Yes? Okay. D. What's your guess?
Squared plus 2.
Okay. I hope you guys are guessing with them, right? You guys doing the guess. Okay, if u is x squared plus 2, then what's du? 2x dx, yes?
What's the point of doing that second part if we don't use it?
This part right here,
Yeah, do we use it?
we're going to use it here. Every problem up to this point, I've said make sure everything matches up, yes? And what's all of a sudden happening?
It doesn't matter.
It's not quite matching. Now, the important parts are matching, aka the variables are matching. What's not matching? The number, the coefficient, which means that's easily fixable. That means we're okay, we're still on the right track. Okay, so what I need to see here, okay, right here, I see my x squared plus 2, right? So we're going to have u to the 3rd. And then we're going to have x dx. I over here have 2x dx, yes? So my recommendation is let's divide the 2 away from the x dx. In other words, let's make this so that x dx, which is what I need, is what I have. And if I divide that 2 away, you can write it as one of two ways. It's what? Du divided by 2 is x dx, which is how some people write it. I'll be honest, I tend to write it as 1/2 du is x dx. You realize those are the same, yes? I don't have a preference as to how you write it. It's a matter of of how we deal with this. So when I go to replace x dx up here, I'm no longer just replacing it with du. I'm replacing it with du and a 1/2, or a divide by 2. Okay, so what you'll usually see me do is replace it with a 1/2 du, in that 1/2 is a constant which I can pull where? Out front. Okay, And here. And even if I just put the 1/2 du right there, it doesn't matter. Because when I write this integral, I want that 1/2 out front. Because 1/2 is just a constant, right? I don't need it in my way throwing off my antiderivative. So when I write this, I'm going to write this as 1/2 times the antiderivative of e to the third du. Okay? Are we there? Notice everything matched, right? I compensated my x dx. I had to balance it. That's why I had to move that 2, but everything else is good. So 1/2 is staying out front. The integral of u to the third. 1/4 u to the fourth. Put that together and plug your u value back in. So 1/2 times 1/4 is 1/8. Replacing u with x squared plus 2 raised to the fourth plus c. Okay, we did not get very far today, did we? Yeesh. That means we have a lot to do tomorrow. E and F, you might try. See what you can do with them. Okay? Because E and F are very similar to what we've been doing. So you might try E and F, look at them. Try them while they're fresh in your brain, because I'll probably have you guys try them tomorrow at the beginning of class while I'm getting attendance and whatnot, if I don't forget. And then we'll go from there. Some of these others tomorrow are tricks. You know, when you start getting into trig function, you sometimes have to employ some tricks. And then we also have to talk about when there are definite integrals, so when there's upper and lower bounds, how we deal with that. Do we want to stay in terms of u and change our boundaries, or do we want to go back to x's, which both are acceptable? And then long division and completing the square were really tricky ones.
Did you say long division?
Yes.
No.
Okay, but
Now, I'll be honest, the long division, I've done all the homework so far, and the long division is very minimal.
Okay.
And actually, sometimes you can use synthetic division in some of these too.
I feel like I need a more review over synthetic division.
Exactly.